Good day to you. This is Anagalactic on Easter Sunday, and this is our second presentation today. If you did not see the prior 1/2 hour presentation, it is of no concern. I make my videos self-contained, which does require a brief synopsis of what went before. What we're currently studying, you may be able to guess by what's over here, the essential David Bohm. If you have never heard of David Bohm, it's probably because you haven't immersed yourself in quantum mechanics. He's one of the foremost authorities on that subject. This is a peculiar book. It is edited by a man named Lee Nicol, and the reason I say it's peculiar is because of some print you may not be able to read fully down here on this line, but there is a brief preface by His Holiness the Dalai Lama, who considered David Bohm to be one of his scientific gurus. About a year ago, I gave a presentation on that, which included the text of what the Dalai Lama says in one page. But what we're going to do today is integrate a few frameworks, which is going to be of enormous assistance to us in attempting to deconvolve the quantum paradox. The quantum paradox is a term that is not heard nearly as often as quantum mechanics, a term I know you've heard. There is also a specific term which I brought out in the prior presentation called quantum theory. And there's another book, well, there is a book by David Bohm called Quantum Theory. This is a 600-page book where David Bohm in 1952 set out in this book to do something for the subject of quantum mechanics that had never been done successfully. And he attempted to be the first, or a pioneer at least among others, in attempting to explain in some way what is quantum mechanics. Now, you may balk because there is a lot of hype at the cutting edge of science in any department, certainly in cosmology, but you would also expect at the cutting edge of going in to the atom, and then beneath the atom is the proton and the electron and, of course, the photon. It is mostly the electron and the photon that induce the quantum paradox. And why? It's because we're trying to measure something that is so small that it disappears, but it's still there. And that's called a waveform. The reason why it can't be measured is because it's not a particle. So you may have heard of the quantum mechanics originally, as indeed I did, as the wave-particle duality. Now that's a very significant term to use, is a duality. It has several related meanings in various contexts, all at the cutting edge of science. Probably the first use of the word duality, without maybe that word having been used, but the concept of duality is of course a two-ness, but it's not binary. And that is actually the subject of superpositional logic, which in quantum mechanics is superpositional state. So superpositional state logic is the fundamental principle guiding quantum computing. So I'm throwing out a lot of ideas here to give a pretty good wide view, a good wide perspective of what it is that we, that is the physicists, the mathematicians, and laymen, we're all in this together now. Well, we always are. Science is collaborative, communicative, consensual. It's shared. It's communicative. It's not private unless it's industry. All right. So what is this paradox? It is called that, but not often because it's kind of negative. Well, as we found out in the last presentation where we covered a professor's view, an accredited professor of quantum mechanics, who wrote a textbook on it, which is quite well received. And we found out what he says in the opening 2 pages of his preface, what is quantum mechanics? Bohm did the same thing, and he tried to cover it in 600 pages, in which he claimed that he was going to try to avoid the mathematical intricacies. And he absolutely failed. Absolutely failed. So what we look for, you and I as laymen, in the process of science, in this case in quantum mechanics, is what is the problem? How was it discovered? That is, the measurements that led to this situation. And somehow describe what the situation is. Well, that's actually the problem. And it's difficult to state unless I encourage you now to just open your mind a little bit to me. You're going to have to trust me because I'll show you as quickly as I can. Just a few sentences. Just what is the situation? How could you conceptualize quantum mechanics, either to yourself or if you had to answer the question, what do you think it is or what is it? Here's what it is according to David Bohm and to Griffin and to Richard Feynman, and really Albert Einstein has his own view that matches, Paul Dirac has his own view that matches, Bohr has a view that matches, Schrödinger, Heisenberg. They all say essentially the same thing, but it is the hardest thing in science to say. You're trying to describe that which you cannot understand. Quantum mechanics is non-understandable. That's the problem. So to state what it is requires some kind of strategy. Well, I have the ideal strategy for that for someone who's not a paid scientist, not an engineer, not a mathematician, not a teacher. Just someone who wants some... Can anybody say anything about this amazing paradoxical system? What is its nature at all? It has to do with tininess. That's the first thing that must be realized. Is as we probe inward to the molecular level, which is about the 19th century, and then the atomic level is the 20th century, and at the same time that the atomic system was discovered by Rutherford, Thomson, and a few others, Bohr, of course, they're progressively trying to interpret the new data based on new technology, an ability to probe further inward, where it was finally discovered what is the atom. The nature of the atom had already been intuited in the construction of the periodic table, which predates quantum mechanics by quite a bit of time. And it was already realized that there was an atomic level, but nobody had ever probed the atom. It could not be isolated with the amount of technology available. This is a technology-dependent discovery because of the tininess of the phenomena. Although much of quantum paradoxicality was already being encountered because of the wave nature of light. Don't forget that Newton thought of light as corpuscles, which means particles. But the wave-particle duality is in fact a duality, which is a mysterious concept. The best example of a duality, in my opinion, just to get some handle on what in the world does that mean. Well, it's not binary, it's combinative. It's two aspects of the same thing, wherein one does not exist without the other. Now, we've already seen that in logic that same duality occurs in the idea of analysis and synthesis. And there's a parallel duality called deduction, that's Sherlock Holmes, and induction. And if you check how Sherlock Holmes actually performed his logical, wizardry, it wasn't deduction. It's always a combination of deduction and induction. They're never separate. The same with analysis and synthesis. And there is a relationship between the two which can be defined. For instance, are they invertible? can you go from analysis to synthesis in the same way you can go from synthesis to analysis? The answer is no, they're ordered. And in induction and deduction, it's the same thing. Without going into great detail on that, I'm merely showing some examples of duality. And electromagnetism is a perfect example of a duality discovered by James Clark, or James Clerk, depending on if you're American or British. It is an E, so Americans will say clerk, but the British say Clark. That is, he was a Scotsman. The language he spoke was English. So, and some people, you always give their middle name, and James Maxwell is one of those. He discovered the duality relationship in light, and he called it electromagnetism, which has been fully substantiated. That is correct. Light is actually a form of electromagnetism. And you could say, therefore, that electromagnetism is in some way related to light on some kind of inversion. Like if you knew what light was, the way we now know what light is, to a threshold, would you be able to deduce the presence of the electroforce and the magnetoforce and the relationship between them? You would. You would know immediately what that is, but they are two slightly different realms. Electromagnetism comes in two forms, and one of them is light. The other one is electromagnetism. And so light is not properly the same thing, although it has been proved that they are the same thing. And that's called superposition. It's a specific form of superposition which has a lot to do with duality. Now, again, I'm throwing out a lot of abstract terms. The reason for doing that is that in the correct approach to a problem of this kind, to define what is quantum mechanics, you can't do it analytically, because the whole problem is that analysis fails. As you go in to try to measure the atom, it becomes increasingly difficult to measure anything inside the atom because it's smaller. So you have to be able to take a measurement, of course. And technology has been advancing geometrically. That's one way to say it. I could say it more precisely, but it's basically hyperbolic. The technology is, in the 20th century, just skyrocketed off of all charts. It was unpredictable just how much we would know in a short period of time. We have not caught up with what we actually do know. And that's what I do, is catch up. So, what we have is a set of measurements. And Bohm brings this out quite clearly, and so does Griffin. That would be our professor and our physicist, who cover both sides of the fence together. Because you do have to look at this in two ways, and this is exactly what Bohm and Griffin say, as typical examples of how men have approached this paradox. You need to be able to state how it was discovered. That is, where did we run into a problem? Where did the physicists find a break with classical mechanics? It turns out even that is difficult to pinpoint. And it's rightly pointed out that quantum mechanics is not the development of a single man. It's been a collaborative effort, at least in the first half of the 20th century, is when I would say 90% of everything happened. Just to give you a ballpark estimate of the ratio. And what was happening in the first half of the 20th century, along with the discovery of the universe with telescopes, don't forget, this is simultaneous with the discovery of the atom. First, the electron was deduced, essentially by Maxwell. But then the proton was discovered. And the proton, of course, is a particle. But light is never a particle. That is what was thought at the time, but then Einstein, who got a Nobel Prize for this discovery of the photoelectric effect, proved that in order to even know how light is absorbed, it must become a particle. And essentially, that's the quantization of energy, which Max Planck discovered, but even that is fuzzy. He discovered what was called the quantum of action, and it was a kludge. It was not something he wanted to introduce into his equation for thermodynamics to solve the ultraviolet catastrophe of the black body problem. And that was thermodynamics, which doesn't directly relate to the study of electromagnetism. But we're talking about the electron, which also was conceived to be a particle, but not at all like the proton. But then Bohr was able to reach a new threshold in the scientific understanding of the relationship between the proton and the electron, which is now very well developed into a very robust, not theory, but model in the good sense. In other words, a lot of information was synthesized by Bohr in a most productive way because he discovered the shell system, replacing what is often called, rather oddly I think, the plum pudding model of electrons were just in a pudding around the protonic core. Because don't forget, the core can have more than one proton, and when it does, it develops the periodic table of elements, which is quite logical and geometric even. So there is a geometry to the atom. But nobody could quite figure out the exact relationship between the proton, which was known to be at the center, 1 to 100 protons. Uranium has 92 protons. By the way, this is the counting system of the universe. The universe counts using counting numbers with protons. So the proton was a major discovery. It's the center of the atom, which is a unique position. Nothing else can be at the center, except there's somewhat of a paradox because more than one proton can be at the center. And that's what's being studied at the cutting edge using the Hadron Colliders today. And they've obviously failed and will not make any further progress. So that's been known for decades. But that will not stop because it's a government program, so we're not going there. So that was very, very powerful, Bohr's discovery of the shell system, because what does that say? It says that the shells are quantized, which is a quantization of the wave. Now, I've proved that, and you don't need to credit that because you'd need to know the proof if you've seen my previous videos to the sufficient extent, then you know I've proved it. But if you doubt that I've proved it, you're doing the right thing, because don't believe a man until you see the proof. Because you're not trying to believe the man. You're trying to believe the reality. That's what a scientist does. So, how far did we get after Bohr? Well, the main discovery of Bohr was the correct geometry, which I probed to an enormous, or I should say an intensive degree, to capitalize on the discovery of a new geometry. And I'm just saying new in the sense that nobody had ever really seen a spheric system like that, where if you have one proton, which is of course the simplest case, that's hydrogen, it's a hydrogen ion. And if an electron attaches to that proton, then you get hydrogen. And it's no longer an ion, it's a stable system. And that stability is not easy to overcome. Hydrogen is stable except in the sun, or star, I should say. The temperature ionizes the ions so that they separate. Now that's quite interesting, but it's not to our purpose, because all of that is rather well understood. At least I'll just put it that way. There's a footnote to everything at this level. But I am homing in appropriately on what we want, which is the ability to know, to be able to understand so as to be able to explain to anyone else, including oneself, just what is it? Well, you have to know how it was encountered. So, it was about in the 1920s, I'll just put it that way, about 100 years ago, that the proton-electron relationship was discovered to a most interesting threshold, that all electrons in an atom, no matter how many protons are at the center, go predictably into discrete shells in a certain order. So this is quantization for sure. And what is the quantization? That is, what is being quantized? It's a geometric quantization. We can say it that way because we can see it. When an electron goes into its spherical shell around a proton in a simplex hydrogen atom, without any neutrons, because it can have one or two neutrons. And if it does have a neutron, it's called deuterium. And if it has two neutrons, it's called tritium. They're not as stable. And you would expect not, because there's only one electron, and now there's two particles at the center, or three instead of one. So the simplex hydrogen atom is the basis of studying this geometry. And a lot of extremely profound statements can be made about the relationship between a single proton and a single electron. All protons are the same. That is enormously profound, because all protons form a center in space, manifesting a position in space, which is not quite saying the same thing, because a position, according to Euclid, according to science, a position is not a geometric object. Normally we call it a point, but that's in a coordinate system. You have to say point in a coordinate system. Euclid proved that. But this is not properly a point. Although you must say it's a geometric point, a proton manifests a position, which by definition is a geometric point. What I discovered is you cannot linearize that point. In other words, it's not on a line, and therefore the protonic center, the geometric center, is not a linear geometric center. And that actually leads directly to the solution of the quantum paradox, just given a bit more information. So that's where we're headed today. And I just wanted to read a little bit of this so you know what Bohm thought. This was 75 years ago, not that long after the discovery of the quantum paradox. I'm just going to read this. I don't expect you to be able to see it, but I wanted to show you that I'm reading from a PDF document that you can get for free. I'll be covering this in more depth later, but when I am online again, which could be within a few days, I'll be able to give you links, but I can't provide them right now because I have no internet connection. Concurrent with the development of the ontological interpretation was the evolution of Bohm's philosophy of consciousness. The word I want you to see there is ontological. I will confess that over the years, I've had to look up the word ontological more than once because I simply forget what it means. It's meant to be antithetical with epistemological, and an authority on this subject by the name of Tim Maudlin, Professor Tim Maudlin out of New York, uses these words copiously. He enjoys the word ontological and epistemological, which if you do have a grasp of what those words mean, are powerful words, but I simply had to learn them. So what is meant by ontological interpretation is non-dynamic, which means usually it means the structure. And that's how I interpret it, because it's just a thumbnail. It depends on context. But in the case of the quantum paradox, when you say ontological, it refers to structure, whereas epistemological refers to process. And process and structure are subtly different, but they're related. That's a duality. So it's another example of a duality, which for our purposes as investigators means we need to take two simultaneous approaches to get this at all, which is a strange thing to say. It has to do with superpositional logic. And I have mastered that, having read Paul Adrian Maurice Dirac's book, which should have been entitled that. Superposition is a major insight that gives an interpretation to the kind of duality that we see at the quantum level. We simply cannot understand or even explain or even describe what's happening. And that's the end of science. That's where we have to break through this barrier. That has not been done for a century. It looks like it's out of reach. I will be showing you not only is it not out of reach, essentially we already have the answer. It's just that there's no interpreter of the facts. It has to do with a lack of structure in the approach. And it's the approach to quantum mechanics that actually can finally be deduced to have been the error, is the way the phenomenon was addressed. Because at this level, which is the final level in the universe, this is it, you simply cannot see what's happening with linearity, including linear logic, or linear mathematics, or linear algebra, or calculus, or the complex numbers, or anything Dirac did, or Schrödinger, or Feynman. It simply can't be done. It can't be done in our current state of mind. So this actually is a challenge to the mind, which is quite an interesting statement. So I'm going to complete this reading here so you'll see how this kind of starts to connect. Because it is spooky to the ultimate level, but not just the universe. It's spooky about our mind. So let's look at this. The ontological interpretation was something Bohm claimed to be trying to express in this book, was the structure, not the mathematics. The mathematics is part of the problem. And he admits that, and so does everybody. But nobody has a solution. And so it just remains this thorn in the butt that's absolutely devastating. So there's strong motivation to get the right answer. And nobody is even approaching the problem correctly. David Bohm was a maverick. And I strongly recommend finding everything you can about David Bohm. An amazing man. He did not get the answer, but he set off, after having become the top of his field. Einstein acclaimed Bohm. That's not common for Einstein, okay? He didn't like the quantum paradox. He said there had to be a mechanical solution. And it's somewhat ironic that quantum mechanics is called what it is, because it's exactly not mechanics. It's non-mechanical. It was Bohm, in his preface in the book I just showed you from 1952, who outlined quite cogently the 3 violations of classical mechanics encountered at the discovery of the quantum phenomenon, or really phenomena. The first thing that was violated was the notion of continuity. The second was the notion of determinism. And the third, see, without continuity, you have to have quantization. Well, that's exactly why the word quantum is used. It's the opposite. It violates continuity, which just alarmed the physicists of their day, including Max Planck, who hated his discovery till he got a Nobel Prize for it. It's amazing stuff, just amazing stuff. But we're homing in on what it actually is. So they're getting down to the ability to measure the position of a proton and the geometric position of the electron in a series of shells. There are 7 of them. Could be extended to 8 because there are some artificially created elements all the way up to 119 protons called oganesson, if I said that right, which also has the most number of neutrons of any nucleus, but it's highly unstable, as you would know if you knew atomic physics. It's just basic knowledge. In fact, that's why we got the uranium bomb and the plutonium bomb, the 2 original fission bombs, is because these nuclei just fall apart by themselves. All you have to do is hasten that, and you get a chain reaction of falling apart. That's fission. Fusion is much different, and we're coming to that pretty quick. But you can see there was strong motivation to utilize the knowledge, such as it was, about the atom for various purposes, I'll just say, one of them being a uranium bomb, which was dropped on Hiroshima, and a plutonium bomb, which was dropped on Nagasaki, and that was the reason for dropping 2 bombs. Only one was necessary to end the war, because the Japanese were ready to quit anyway. Huge controversy about that, of course, because it's politics, government, and warfare. Well, we're stuck with that, but not here, not in our department. We're not stuck with anything. Now, once that geometry was discovered, which is quite profound because now you know where the electron is. Well, actually, that's the beginning of the problem. Using coordinate extrinsic geometry, it was easy to position a proton because a proton makes a position in space, which is a very interesting thing to say, that it makes a non-Euclidean point. It makes a spheric point, which is non-Euclidean. But in order to plot it on a Cartesian graph, as we do in 3D and 4D, it has to be a linear zero center, which is, I'll just say that's structurally wrong. So it's correct to say that there's a position at the center of the proton, but not that it's a Euclidean point, because it's not on a line. It's at the center of a sphere, which is at the center of a different kind of line, which I hope you're struggling to visualize, because this is what you need to do. But I'm not going to leave you hanging. We're going to get the answer. It's just this is the right way to get the answer. That the proton is the source of a new geometry, which is spherical, not linear. Well, I discovered that, but now you have to go forward. Let's do so now. What's the atom? Well, in the simplex hydrogen atom, you have the center, which is a force field. Because in order for there to be a geometric center, what otherwise would be called a spherical point, which is a geometric point, which we haven't defined yet, except roundaboutly, it's the center of a spherical force field. That is known. But the nature of the force field is not known at all. Not as much as we'd like. So where does the electron fit into this central sphere that forms a geometric central point? That's 2 different definitions of center. Is it the surface of the force field? Well, the force field does not have a positional center. It does, but it's not the surface. Well, then what is the surface? It's the surface of the force field. Well, that's non-material. That's the spooky action at a distance, is the protonic force field. Well, do we know that that's what it is? Yes, we do. You know why? Because of the behavior of one electron in the presence of that force field. We know that the electron has a negative Coulomb charge, which is considered to be polaric, but you'll find out that that's actually a bit naive. Which seems to, I'm just challenging electrodynamics, not really, because it's superpositional. This Coulomb polaric charge, plus minus, is well established, but it doesn't explain everything. And it has to do with this force field surface, which is non-material. But the only material we know of in the whole universe is the proton. That's the only material object in the universe. Anything else that has material presence, such as the Earth, the Sun, a galaxy, or the whole universe, is due to its protons, not the electrons. So what is the electron? It's tempting to say that it's a particle, but if you're talking about this atom, then the shell would contain the electron, correct? We know there is such a thing as an electron in another context because a linear velocity can be applied to an electron such that it can be fired from a gun. And I would have to say that that certainly makes it a candidate for being a particle. But the strange thing about the electron is when you try to find its position, you can't. It doesn't have a position, ever. Even when it's fired from a gun, it's not traveling the same way a proton travels because they're not structured the same way. Well, what's the difference? One of the differences that we can state at the outset is that the proton makes a force field. It makes a spherical force field around its positional center. That's basic. That is tautological. That is what a proton is. It must have a force field. It does. So what is the force field? How does that relate to the center? That's what the Hadron Colliders are trying to discover. I discovered the answer that the Hadron Collider physicists will never get, which is a profound and provocative statement, but we're leading up to the solution. It has to do with the electron-proton relationship. The electron does not manifest a position in space. Instead, what we can see that it does is it makes a spherical shell where that electron is either everywhere in the shell at once, which makes no sense, or it's nowhere in particular, which makes it probabilistic. It's just probably somewhere. That's a little closer, but it's not good enough for Einstein. It's not good enough for us either. Is it a particle or not? Well, it's not. And that's the answer to a certain threshold, but that remains to be proved. If it's not a particle, what is it? Well, we do know what to say it is if it's not a particle. The only other thing that anything can be other than a proton is a wave. Everything else is a wave. The question might be asked, rather logically, I would say, and this is the time to ask questions, believe me, is the proton a waveform? No one's ever answered that. The answer to that question is unknown. So we have a dual paradox. We're not sure if the proton has a waveform to the proportion that we do not know that the electron has a particle-like position, making it a particle. Is it a particle or not? It's unknown. Is the proton a waveform or not? That's unknown. I'll show you the solution to that. It has to do with the duality involved. But that introduces something that is eluded the greatest minds in the history of mankind, including Einstein, Dirac, Feynman, everybody, have not been able to see the duality that turns out to be equivalent to electromagnetic duality, except for one impossible to see factor. It's an imaginary factor, which sounds like that's outside the realm of science if you're using your imagination. It's not that you're inventing something that doesn't exist. It's that you're using your imagination to compile what the universe says. In order to understand this duality, you actually have to alter your mind. And that is not possible anymore for the mathematical physicists. They cannot see. And that's 40 minutes. We'll have the solution in the next video. I hope you appreciate that this approach to the quantum paradox, which I discovered about 2 years ago, has taken me 2 years to be able to explain to anybody else. And I research every day. I do original research every day as well. And I'm constantly trying to formulate new approaches to this now ancient paradox that has halted science and has ruined science, because we have enough information now to get the answers that you and I want. We'll talk about that a little further. What do you want from this? If it's entertainment, I would have to say you're probably going to get it, but only if you actually see why this is important. Otherwise, it won't be entertaining at all. You'll just pick up some new factoids, which may or may not be true. You'll never trust me. You won't care about the proof. You just hope that I stimulate you in some way. I will, but the only way that I can stimulate you is with the solution that I've proved. So this is my latest approach to expressing the solution to the quantum paradox that unlocks physics. This is Anagalactic, bringing you the secrets of the universe. Stay tuned. We'll be back online within a week, I pray. And we'll pick up where we left off, and then I will be going into live streaming, because I will have a broadband connection for the first time in a long time. And you have to have a broadband connection for live streaming. And then we can interact. And that'll begin a new phase of science, which will revolutionize the world. Don't count on that literally. That's me using my imagination for what should result. But what should result in this present world is not what's going to happen. Except at the periphery, a few selected individuals, myself being the first, will understand the universe to the threshold that humanity wants to know, to solve our ultimate dilemmas in existential reality. Consciousness and reality. Stay tuned. Don't miss the next few lectures. It's the result of an enormous amount of work, not just mine.